Okay, so today I was thinking to go through all whatever we left, right? So if you have anything from your any of the from the rest of the lectures, we can just you can just tell and we can pick that up. So for example, we completed up to this porphyroblast section, right? Hello. We did not cover the Budinaj, right? See, I can't check the chat each time. If you communicate verbally, that will be better for us, right? So if you communicate verbally, then so what was the last thing that we discussed? Anyone? What is happening? Can you hear me? Can you hear? Can anybody hear me? Prabhakar, Pramod, Suraj, Velmurugan, Jayasuriya. Can you hear me?
Yes, sir.
Yeah. So I was asking, what was the last thing that we discussed? So you don't.
Sir, cannot remember.
Okay. I think we discussed this fold lecture because that is what I can see in my OneNote. Can you see the OneNote? So these are the things that we discussed, right? Axial planes and all these things, right? In the 9th class, and deep isogons, right?
Yes, sir.
Okay, yeah. So yeah, so these are the things that we discussed, right? So today I will go straight to the Budinaj and then I'll just skip some part of it because Budinaj is more or less straightforward. So, so what happens in the case of Budinaj, that in natural rock you have different kinds of materials, right? So it happens, right? Like in the material that which is sandwiched by this black material, which is sandwiched by this yellow material, it can happen that the competency or the viscosity of this material might be different from this yellow one. So what happens if this material is less competent, that it is more stiff than the material which within which it is embedded in? What happens with application of extensional force? It can it snaps, right? So, and it's just like breaking a potato cracker or breaking a chips, right? Potato chips, the lays, right? So something like that. So it breaks, right? And what happens is that, so these material outside, these are more competent, which means it will flow inward. Can you see there is a little bulge inside? Can you see this? Can you see this bulge? Please respond if you can see the bulge.
Yes, sir.
Yeah. So so this is what happens in case of a Budinaj, right? So so the material outside, it goes inside and makes a layering, just in inward making an inward curvature, and the material which is more stiff, it just breaks off, right? So if this is the extensional direction horizontal to the so what is the plane that we are watching the Budinaj from? So we happen to have some idea about the coordinate systems of the force fields, right? So if this is the vertical section, the vertical lines, these is the compressional direction, and this is the extensional direction. So what is this horizontal direction called? Is the direction of maximum elongation, right? So this is called x, right? This is x direction, right? And this one should be the z direction, right? Because in the xz direction, in the xz plane, you get the maximum deformation signatures, right? Are we clear? Hello?
Sir, once again.
Okay, yeah. Just suppose what is happening here, you have a layer like this sandwiched by a different material. So this material outside is different than this one, right? So there is a viscosity. We know what is viscosity, right? Mu. So mu1 and mu2 is different. So mu1 is must be very high, right? So in that case, what happens if you apply some kind of extensional force? I mean, in the nature, if this force is applied to this rock mass, then what happens? It will extend, right? It will extend in these two directions, right? So as a result of that, this material will also get stretched and this material will also get stretched, but the rate of their strain, the rate of the strain rate will be different, right? I mean, the speed at which this layer can accommodate strain, these layers can accommodate strain will be different than the rate at which this layer is accommodating strain, right? So the strain rate for this layer will be different than the strain rate for this layer. So as a result of that, there will be a relative displacement, right? So this thing will break, right? So because it is, so the friction in these layers will be very high. Let's not go into that. Okay, so if you stretch the material, what will happen? Just like a dough, when you make a roti out of a dough, right? So when you just like a dough, this upper part, the upper and the bottom part, it will get stretched, and the lower part, I mean the in the middle, whichever part you have there in the middle, it will just break. So it will form little pieces like this, right? Very sharp edges like that, right? And so this material has the this material is the less competent. That means it cannot adjust with the variable strain rates, but the material which is outside, it is more competent, so it will flow inside, right? So there will be new gaps will be produced, right? And this kind of layering we can see in nature, right? See, this will happen. And these kind of structures, which are extensional features, are called Budinaj, right? Is this clear now, how Budinaj forms?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay. So so this is, so I was telling that this is the x direction, right? Because this is the direction of maximum elongation, right? And this is the z direction, because this is the direction of minimum elongation or maximum compression. So these are synonymous terms, right? Because whichever is not in the elongation domain, I mean, which is not getting lengthened, so we can, so it's a minimum, so we can call them as the direction of compression, right? So but what happens in case of 3D? So we know, right, what is the plane of a foliation. Suppose foliations are getting developed in this particular plane, right? So this is a foliation plane, right? So what happens in case of that? What is this plane? How are the axes are oriented in this case? These are foliation planes. So how are the axes oriented in this case? What is this plane called?
X-axis.
No, what is this? So see, a plane should contain more than one axis, right? So you are right that it will contain x-axis, and what is the other axis? This is the z-axis, perpendicular to the foliation, right? Because if you compress something in this direction, then only you will get the foliations on the perpendicular to that direction. So this is the compression direction. So this is z-axis, right? So what is the other axis? So one axis should be x. What will be the other axis? Z is here already. So here is z, perpendicular to that. So this is x, this is something else, this is z. What is this axis? This is y-axis, right? So is there something that is not clear? Hello?
Yes, sir.
Yeah, so is there something that is not clear? Why this is the y-axis? Hello? Are you with me? So you can tell, right? If you have any doubt, you can tell. Just tell me, because this is the time when you get your doubts cleared, right? Okay, so people are leaving. Suraj Velmurugan Jayasuriya.
Yes, sir.
Yeah, so I am asking if you have, are you getting what I am telling you, right? What I'm trying to teach here, like why this is the XY plane. Are you getting? Hello? Yeah, so are you getting this? Why this is the XY plane? Because otherwise I can't explain how the chocolate budinage forms.
Yes, sir.
No, what? Yes, sir. I'm just I'm asking. I want to know. I really want to know if you are getting this or not. Why that is the why the foliation plane is the XY plane? Are we getting? Are we clear on that? Okay, I'm going over this again. Suppose you have a homogeneous rock mass, okay, and now you are applying compression from here and here. So how will the foliations form? Will the foliations form like this or like this? How will the foliations form? What is happening today? I don't know. I mean, I am asking how will the foliations form if you have a uniform rock mass like this, and this is say for example some kind of rock, okay, and you are so there is some natural force, so this applied in this direction, this is the z axis, right? So how will the foliations form?
Sir, parallel to XY plane.
Exactly, parallel to xy plane. So the that means that foliation planes are xy planes, right? Right.
Yes, sir.
Okay, so foliation planes, so everyone got that? Why foliation planes are the xy planes?
Because only vertical force act.
Yeah, so in the z axis you are applying the force, right? On the z axis you are applying the force. So the material cannot flow on the z direction. The material will flow perpendicular to the z direction, right? So applying force from the z direction, the material will flow. If you are applying force like this, so the material will flow in these directions, the perpendicular to the z axis, right? That's why the xy plane is the foliation plane, because those are the two directions where the material can get stretched, right? So I just explained you how chocolate budinach, how budinach formed. So now imagine these things are happening in 3D, right? So Z is the compression direction. So vertical direction is the compression direction here, and XY plane is this plane. This gray shaded plane is the XY plane, right? So as I said, like this, these are the two directions in which you will get the extension, right? So the x and y both are the fields of extension, right? So the material will also get extended at the x direction, and it will also get extended in the y direction. So that's why you will get these gaps in both these directions, and you will end up by having this little squared blocks, or not squared, maybe rectangular blocks. So these type of structures are called chocolate budinage. Okay. And so this is a natural example, right? And it may not be always parallel, perpendicular, the x and y. It can have a little bit angle like this. Maybe it can happen due to two different stress regimes, right? So one deformation event and the second deformation event, it can happen like that. So what is pinch and swell? Pinch and swell, like so why Budinach form? I just explained that Budinach form because of the competency contrast, right? So if the competency contrast is less, then the less competent layer will also flow, right? It won't make these sharp edges that you see in the usual cases of Budinach. So what will happen? So along with the material outside, along with the outside material, light green material, it will also try to get, it will also neck, just like when we all see like our mothers or in our home when they make rotis, chapatis. What you do, they just make one, separate one little balls out of this long dough, right? So these necking and the flower or data, that also makes that kind of necking structure there, right? It's the same like that one. Okay. Okay, so this is a natural example of pinch and swell structure. Okay, yeah, so this is the origin of Budina structure. See, this is the compression direction and this is the extension direction, and it will just break along these lines. Okay, so we just saw that simple like the budinaj are forming in beautiful rectangular shapes like that, but that is not the case in nature, right? In the nature, there is always one thing that is called rotational component, right? So suppose there is a shearing along this extension. So what will happen? What is the rotational sense? The sense is clockwise. What is this sense called? Is it dextral or sinistral? Is it sinistral or dextral? Sorry, I can't hear you.
Dextral.
Yes, that is dextral. So see, depending on the shearing, the budinaj can rotate, right? But if the rotation of the budinaj is same as the what should I say, is same like here the rotational component, the shearing component is sinistral, but the budinaj is rotated in the dextral orientation, right? Is rotated just like that, right? And the rotational component, the shear component is just the opposite. So then we call that antithetic slip. And if the rotational component and the budinaj here and the shearing in between the budinaj and the rotation of the small blocks of budinaj are all in the same direction, then we call them synthetic slip. All right.
सेम डायरेक्शन तो सर उसमें नहीं लगा, उसमें भी ऑपोजिट ही डायरेक्शन है.
No. See, okay, I'll just show you this also. See, these blocks have rotated in the just imagine these blocks. I mean, just see these blocks, right? It's just shifted in the right hand side, right? So how will you get that? If you rotate that dexterally, then you sorry,
clockwise direction rotation
clockwise, then you will get that, right? But the shearing in between the budinaj blocks, see, that is anti-clockwise.
Yes sir.
So that's why it's called antithetic slip.
But दूसरे वाले में भी opposite ही है.
Yes, these are
No.
See here, yeah, दूसरे वाले
both antithetic
yes, both are antithetic.
Oh, yes, तब ठीक है सर.
Okay. So these are some say suppose there might be no slip like the usual one that I usually drawn previously, drawn budinaj drawn. So these are some different kinds of budinaj classification that people have done from different natural observations. I mean, in any way the budinaj can form, right? So yeah, so these are the torn budins, the shear band budins. Yes, there are lots of classification. You can just go into that and okay. So this is what happens when you have different kind of say weak planes on the less competent layer, and the difference in competency contrast. So these things actually control, mainly the competency contrast. It controls what will be the shape of these budins, right? If it's very high, then the edges will be very sharp. If it's little bit low, then it will be barrel shaped. If it's much lower, then it will be like that. So these are some different so all of these budinaj structure may not be always available in the nature, but people have done experiments to simulate these things, and you will see these experiments. So different kind of with aspect ratios of the budins, they have performed these experiments, and yeah, more or less that. And yeah, so what they have done, they have changed the initial flaws, right? So whenever they change that, initial fractures and make some kind of angular relationship with the give the some angular relationship with the initial foliations, then they whatever result they get, they try to mimic that with the natural bodinage, right? Yeah, so this is the chocolate bodin that I just told you. So this is the strain ellipsoid. Yeah, so in the fold we can also get the bodinage structure because the hinge remains in the compressional setup, but the limbs, like these limbs and these limbs, they always remain in the, why it is not getting clear. Okay, so these remains in the extensional zone, right? So you can get bodinage in along the fold axis, or you can get two sets of bodinage, right? Uh, yeah, so this is more or less the repetition of the previous lecture. Let's see. Yeah, okay. So anything from the bodinage chapter? Hello, anyone?
Sir,
No, sir.
once again say in the synthetic S-type bond niche.
Sorry, sorry. Which one?
Synthetic type, S-type.
Okay. So antithetic, you just understood, right? So what is the shear sense here? What is the shear sense here? Sinistral, right? And what is the rotational direction of the bodines? So this is antithetic or A type, right? But if you get a bodinage like this one, then it is also rotated in this direction, and the shear sense is also in this direction, right? So if I right, in that case it will be synthetic, right?
Okay, sir. Thank you.
Okay. Okay, so let's go into the fracture part. Fracture is basically what can I say, a kind of brittle deformation in which a material just loses its cohesion, right? So in the brittle ductile failure, so there are some equations through which we can actually predict if we have the value of this S and mu. And so this is pore fluid pressure, this is normal stress, this is shear stress. So if we, so these are material properties, mu and S. So if we know these things, then we have an equation, a relation with the shear stress, normal stress, and pore fluid pressure, right? So depending on the different kinds of material, this relationship changes, right? Because this material constants change. So these two values change, and so this whole relation changes. So that makes the difference, like at a particular load and pore fluid pressure, when so some material will fail and some material won't fail. So it only depends on these relationships, all right?
Sir, I have a sir question.
Yeah.
So what is basic difference between cleavage and fracture? सर हमेशा से ये मुझे confusion रहता है.
Okay. So cleavage is a term which is usually called, suppose, is associated to the rock cleavage, right? So suppose you have any kind of discontinuity when you have say for example a hiatus in the rock strata. So there's a kind of series of breaks, right? So those you call them cleavage. But in fracture, when you have like there is not, so fracture is more or less a generic term for any kind of gap or any kind of discontinuity. We can call them fracture. So in the mineral you call them the fracture. So in the outside, when the fracture might be sealed, the fracture might be opened, right? So a fault is a fracture plane, right? So everything in geology, every discontinuity, any discontinuity, we can call them as fracture. But cleavage is associated with rock, right? I mean, in a field scale, when you are seeing a particular gap, right, a particular hiatus, then you can call them rock cleavage usually. And with cleavage, we always use the rock before using the word cleavage, right? All right.
Yes, sir.
Okay. Yeah, so these are some experimental setups which you don't need right now. Yeah, so this is the more envelope. So shear stress is a function of the normal stress. I just showed you. Like, so these are the solutions. Okay. Yeah, so this circle can be constructed depending on sigma 1 and sigma 3. So sigma 1 is the maximum normal stress, and the sigma 3 is the maximum and minimum normal stress, right? So using that small circle, so this is the line that is defined by the material itself. You cannot do anything about. So a particular material will have a particular line like this one, right? Suppose this is a line for quartz, so, or quartzite. So for limestone, you will have another line with a different slope, right? So if this is a line of a limestone, then suppose you have a line like this for quartz. So what will happen at a particular sigma 1 and sigma 3, the limestone will produce fracture. And when it is produce fracture, if this circle touches this failure envelope, so if this touches the failure envelope, then it will produce fracture. So a particular sigma 1 sigma 3 combination can produce fracture, right? Suppose you have a sigma 1 sigma 3 which is like this, just smaller than this half circle, but this has a higher value than these circles, right? This sigma 1, but this will produce fracture, but this won't. What I am saying is, well, it's black suddenly. Okay. What I am saying is, so this is a failure envelope for limestone, and this can be a failure envelope of quartzite. So for a particular sigma 1 sigma 3, limestone can produce fracture, whereas quartzite won't, because the subcircle touched the failure envelope of limestone, but it did not touch the failure envelope of quartzite. All right. Now take another example where you have sigma 1 sigma 3 like this, sigma 1 sigma 3, and another case you have another sigma 1 sigma 3, sigma 1 dash and sigma 3 dash. So which one is greater, sigma 1 or sigma 1 dash, which one is greater?
Sigma 1.
Yes, so sigma 1 is greater, and for sigma 3 and sigma 3 dash, which one is greater? Sigma 3, right?
Sigma 3 dash.
No, sigma 3 is greater than sigma 3 dash, right? This is increasing order.
Okay. Oh,
So it doesn't necessarily mean, so these values are greater than sigma 1 dash and sigma 3 dash, right? These values are greater than these values, but the limestone will fail for this combination. Why is that? It will fail for this combination, not for this combination. Why is that? Because this combination touches the failure envelope, right?
yes, sir.
Okay. So there's some other criterias when you will have different kinds of equations, different kinds of lines. For Wake Brown, instead of a straight line, you get a failure criteria like this. You get a failure criteria like this. Okay. So this is the plot in that case. So in Moore Kurlab, you get the straight line. In Wake Brown, you don't get the straight line, and there are other criterias as well. It depends. Like so these are all empirically derived formulas, right? So there is no proof that this is the this is the Wake Brown criteria. So this is not the actual. It may not be the actual failure criteria after all. This is the Tresca failure criteria. So whichever applies for a particular rock. So there are different scientists, different people, they design these different criteria to suit for which they found suitable for a particular kind of rock. Right. So there is one Mises failure criteria. You can just go through that and just read like why these are necessary.